Okay, dear students, today in this session we will observe the concept of trees. First, we start with the definition of a tree. So we'll observe what is a tree and what are the properties of a tree and different types of trees based on the degrees of the vertices that we have in the tree. Okay, so first we start with the definition of tree. So what is a tree? So a graph G with vertex set V and E is the edge set. In a graph we will have vertex set and the edge set. The definition of a graph. So a graph G is said to be a tree if G is connected and the second point, there are no cycles in G. It doesn't contain any cycles. Okay, so G doesn't have any cycle. So in simple words, how you can write a connected graph with no cycles is called a tree. In this way, we can write easily. A connected graph with no cycles is called as a tree. Okay, first what is a connected graph? When we can say that a graph G V comma E is a connected graph if there exists a path between every pair of vertices in the graph, then we call it as a connected graph. So first you must have the clarity about what is a connected graph. Yes, what is a connected graph? If there exists a path between every pair of vertices in the graph, then we call it as a connected graph. Okay, so cycle, you must know what is a cycle. Okay, so in the name you have, so if you observe in a graph a path like this, it is like a closed walk. Okay, so here this is a cycle. Yes, this is also a cycle. It is also a cycle like this, a closed walk. If you observe, that is nothing but a cycle. So, but here you observe, when you can say that a graph is a tree, a graph G, V comma E is said to be a tree if it is connected and it doesn't have any cycles. Okay, then we call it as a tree. Okay, so you observe here a graph containing only one vertex here. So this is obviously mm, connected. Okay, no cycles. Next, if you have a graph with two vertices V1 and V2, and there is an edge between V1 and V2, so this is also a connected graph with no cycles. Okay, so this is also a tree. Okay, these are all examples you can take for tree. Okay, next, so you observe here three vertices. I am taking three vertices V1, V2, V3. So we need a connected graph. So here I am taking the edges in this way. So this is a connected graph because every pair of vertices are connected. That is, there exists a path between every pair of vertices in this G. So this is G1, which contains only one vertex. So G2, which contains two vertices which are connected. That is, there is an edge between these two. So no cycles are there. Next, in G3, we have three vertices and two edges only, which is a connected graph. Because you take any pair of vertices, there is a path between those two vertices. So next, no cycles in this graph, so it is also a tree. You can represent a graph geometrically, not only in this way. You can represent in different way also. So I have taken those vertices in horizontal manner. Now you can take in the vertical way also, like this. You can represent, and you can join those vertices like this. Okay, or you can represent the graph in this way also. So the same graph, but geometric representation, that graphical representation, it is different. V1, V2, V3. That geometric representation is not unique for a graph, Sorry. So V1 is connected, that is there, V1 and V2 are adjacent. Next, V2 and V3 are adjacent. So we should not take an edge here. Take this one. So join these two vertices. Okay. So this is also representing G3 only. This is also G3 only. Okay. So all these are trees. You can take a graph with four vertices, which is connected and doesn't have any cycle. You can call it as a tree. So you observe here a graph with three vertices. If you take three vertices, so see this one. So V1, V2, V3. So here also this is a graph with three vertices. Okay. So is this G is a tree? Yes. Is G a tree? G is a tree or not? It is not a tree. Okay, G is not a tree because so here in G we have a cycle. There is a cycle. So it is not a tree. It is a connected graph. G is connected, no doubt in that. But it is not uh, a tree. Why it is not a tree? There is a cycle in this graph. There is a cycle in this graph. Okay, so it is not a tree. Okay, so if there is no cycle, you can call it as a cyclic graph. Okay, if there is no cycle in a graph, a cyclic graph. Okay, then we can call it as a cyclic graph. Okay, next here we observe some properties. So see some properties of trees. So the first and very important point here, a connected graph with n vertices and n minus 1 edges. N minus 1 edges is a tree. Okay, so a connected graph with n vertices and n minus 1 edges is a tree. See that. So this is very important, connectedness. A connected graph with n vertices and n minus 1 edges is a tree. So we have a theorem also on this. We'll observe that proof also. So if you take this same as some theorem statement, so take it as a statement. So we prove this by contradiction. So proof of this statement. let some G, V comma E be a connected graph with n vertices and n minus 1 edges. Okay, so then when you can say that a graph G is a tree, it must be connected and it doesn't have any cycle. Okay, a connected acyclic graph is called as a tree. So what we have to show now, you are taking anyway connected graph. So we have to show that there doesn't exist any cycle in this graph. Okay, there doesn't exist any cycle in this graph. So here I am assuming let there exists a cycle in the graph G. Let there exist a cycle in the graph G. Okay, so here in the graph G, V comma E, the cardinality of V is n and the cardinality of E is n minus 1. Like that we are taking. So we are taking the graph with a cycle. So I'm taking the proof using contradictory method. So see this, I'm taking a cycle in this, then what will happen? You observe. Okay, so see this. These are the edges I'm taking. So observe there is a cycle in this graph. So here in this graph, we are taking n vertices and n minus 1 edges actually. So here I am considering an edge E here in this graph. So consider an edge E. Okay, so if you observe that edge E, and if you delete the edge E from the graph G, so that is, I'm taking the new graph G dash such a way that by deleting an edge E from that G, where I'm getting G dash. So if you delete this edge from this, then how it will be? Because it is a cycle, like this. For example, you observe if you have a cycle in this manner. So if you delete an edge from this cycle, so if you are not having an edge, for example, so see this. So see this one. If we don't have an edge here, see this. So if I remove that edge from that cycle, this graph is a connected graph only. It is not a disconnected graph. By removing an edge, some specific edge here in this cycle, maybe any edge you take, not only the specific, so any edge here from the cycle, the graph will be the same. It is a connected graph. So then G dash is equal to G minus E. Okay, so will be a connected graph with how many vertices we will have by removing that E. You are removing or deleting only an edge from that graph, but you are not deleting any vertex. Okay, so there will be no change in the number of vertices with n vertices and n minus 1 minus 1 edges. Means already in the given graph, how many edges you are taking? N minus 1. So from those n minus 1 edges, you are removing one edge here. Means so totally this is nothing but n minus 2 edges will be there in the new resultant graph. Okay, so by deriving an edge E from this, you are getting this new graph. So here we are having a graph with n vertices and n minus 2 edges, and it is a connected graph. Is this point is correct or not? This point, is there exists a connected graph with n vertices and n minus 2 edges, n vertices and n minus 2 edges? So actually this point we all know and discussed when we discussed about connected graphs. So with simple example, you can observe this point here also. So that is, see this one. So simple graph, I am taking a connected graph with how many vertices? 3 vertices. So A, B, C. A, B, C. So this is complete graph and it is a connected graph also. No problem with that. Okay, but here you have n vertices and n edges. But what is the case we are taking here? So please observe that point, Amma. So now our case is a graph G with n vertices initially G. You observe that G, n vertices and n minus 1 edges. So here n is 3. So is it possible to draw a graph with 2 edges which is connected? Yes, it is possible. So this is a connected graph only. Okay. So if you remove one more edge from this, so that is 3 vertices, then how many edges will remain? Only one edge. So if I remove the edge A to C, okay, then we will have an edge between only A and B. Then you observe, if you remove, that is the case of n minus 2 edges, n minus 2 edges. Please observe, is it connected? No. So if it is a connected graph with n vertices, so then definitely it must have at least n minus 1 edges. So but here you are getting G dash as a connected with n vertices and n minus 2 edges. So definitely this is wrong. So why you are getting that wrong statement? Because of our assumption. So let there exist a cycle in the graph like that. So we are proving this by contradiction. Okay, so we are starting with the assumption that there exists a cycle. So because you are taking a cycle like this, then we are getting this wrong statement. So which is a contradiction to that statement. So but here what you can say, but we know that a connected graph with n vertices will have at least n minus 1 edges. So it is a contradiction. We are getting this wrong statement. So therefore, our assumption is wrong. What is that assumption? There exists a cycle. So there doesn't exist any cycle in the graph, but that graph is connected already. So the graph is a cyclic. So therefore G is a tree. So this is the proof for that statement. So a connected graph with n vertices and n minus 1 edges is a tree. Okay. If you see that proof once, all of you. A connected graph with n vertices and n minus 1 edges is a tree. This is one property that we have. Okay, so next point that you have to observe. A graph G with n vertices and n minus 1 edges need not be a tree. So you know the definition of a tree you observed already. So when we can say that a graph is a tree, it must be connected, yes, and it is a cyclic. It doesn't contain any cycle. Okay, so but you observe here a graph with n vertices and n minus 1 edges. That statement, previous statement, that what we observed, a connected graph with n vertices and n minus 1 edges is a tree. But here, what is that point is missing in this? Connectedness. Connectedness. So is there any example which is supporting this statement? Yes, you can observe that. See here, I am taking a graph with 4 vertices and 3 edges. 4 vertices and 3 edges. See this? 1, 2, 3. A, B, C, D. So here the number of vertices is 4 and the number of edges is 3. So here it is, if it is n, this is n minus 1. So the graph G with vertex at V and edges at E is not a tree. It is not a tree, but it is having n vertices and n minus 1 edges. Why it is not a tree? Because it is not connected and it contains a cycle. So there is a cycle is there, and it is not disconnected graph. It is a disconnected graph. It is not connected. So this is one point that you have to observe. Okay, next, another point. So already we observed that theorem. So in a tree, there exists exactly one path between every pair of vertices. In a tree, there exists exactly only one path between every pair of vertices, not more than one path. Okay, so you can observe that. So it is easily understandable. It is very easy to follow also. So observe this. If it is a tree, it doesn't contain any cycle and it is connected. So I am taking this is a tree. Okay, connected graph, no cycles. Okay, so this is a tree. So I take any two vertices, there exists only one path between those two vertices. But if you take some graph like this, which is not a tree, which is not a tree, okay, see this is some other graph. So I'm taking the vertices like this, A, B, C, D. Okay, then I want a path between A and D, between A and D path. So you can take A to B, next B to D, B to D, or you can take A to C, next C to B, next B to D, or you can write like A to C, next C to D. Okay, so the path is not unique. So more than one path exists. So if it is a tree, definitely between every pair of vertices, there exists only one path. Okay, so these points you have to observe. And if you want to test whether the given graph is a tree or not, you can check this point also. Okay. Next, one more definition here. The next definition it is minimally connected graph. So if you have a connected graph, so if you take a graph G, V, comma, E, which is a connected graph, so we there say that the graph G, V, comma, E is minimally connected if the removal of any edge from this graph converts that G into disconnected graph or makes that G into disconnected graph, then we say that the graph G is minimally connected. For example, you take a connected graph. G, three vertices, V1, V2, V3. I'm taking. So this is a connected graph, no doubt in that. So here, by removing any one of these two edges, okay, so if I remove E1 here, then the graph of this will be like this: V1, V2, V3. I'm removing E1 from this. Okay, I'm deleting an edge between V1 and V2. Then the resultant graph, if it is G, the resultant graph, I am taking it as some G dash. Okay, so here G dash is a disconnected graph. Okay, so then you can call this G as minimally connected graph. Minimally connected graph is a minimally connected graph. Okay, so the next topics we'll observe in the next video. Okay, thank you all.